basic concepts of RAMWind to you. For those of you who attended our presentation at the workshop, this may look familiar, but for many of you, I know you probably are not familiar with it at all. Okay, RAMWind is essentially an empirical terrain wind speed model. It adapts to local conditions at a site with no a priori assumptions on the relationships between the wind speed and terrain. Instead, with RAMWind, we let the wind data essentially tell us how the terrain is related to how the wind speed varies. It's a holistic approach where we like to use all the Met towers at a given site. It is in a combined analysis to collectively indicate the relationships between wind speed and terrain. So we analyze the wind speeds at the Met tower sites in the context of terrain parameters to establish what the relationships are between the Met towers, and then apply those same relationships to proposed turbines at the project site. One of the most important things is to make sure that the wind speed data that is used in the analysis is all cleaned and normalized to a consistent basis in time and so forth. So if you have Met towers, some of which are affected by trees and others aren't, there likely to be an inconsistency between how those wind speeds are represented and so forth. So it's very important to have all the data very clean and consistent in time basis. Okay, the RAMWind terrain parameters, we use one of the key ones is terrain exposure, which is essentially an integration of the elevation differences between a given location, be it a Met tower or a turbine site, and the terrain surrounding it. It's performed in a sector-wise calculation with the specified radii, and the elevation differences are weighted with an inverse relationship to the distance or radius from the point of investigation. And we also use elevation in the analysis. And we calculate these variables from digital elevation data. The upwind and downwind exposure parameters are based on essentially the concept that if the wind is blowing from the north, the upwind terrain would be all the terrain that is from the same direction that the wind is blowing. So for upwind exposure, we look at for the north wind, we look at the terrain upwind and so forth around the compass. And conversely, for the downwind terrain and the north wind, we look at the terrain toward the south and so forth. So for the southerly wind, we would look at the terrain to the north and calculate the exposure variables in that way. We have found that the downwind exposure is a very important parameter in defining how the winds will blow at one site compared to another. This is a cross section of some terrain. If you look at the black vertical line, that represents a Met tower. And in this situation, if the wind is blowing from the left, then the terrain downwind would have positive exposure. And then conversely, if the wind is blowing from the right, then the downwind exposure would be negative because the terrain goes higher. So in RAMWind, positive exposure means that the terrain in a given direction is generally lower, and negative means the terrain in a given direction is generally higher than the location of the Met tower or turbine site. Now we use the terrain exposures in a number of ways. The sector-wise exposures are calculated and can be used to characterize the variance in wind speeds between sites in a refined directional way. And this is the kind of analysis that has been used for wind farm wake analysis, as in the EON wake presentation they did in 2010. We used RAMWind there when other models were decided they couldn't perform adequately, and RAMWind did very well. And then otherwise, we combine the sector-wise exposures into what we call a bulk average exposure, where we weight the sector-wise exposures based on the frequency of the wind directions around the compass. And we use those with mean average wind speeds to in mapping, as in RAMWind version 1 that we have now. And we also are beginning to use this concept in mesoscale mapping. With some of the basic observations we have with RAMWind is that, well, it has performed better than WASP and CFD models in 2 different studies that were presented during a workshop in 2009. We've observed that downwind exposure plays a very important role in determining relative wind speeds between 2 sites. In general, sites with have higher weighted mean exposures tend to have higher mean wind speeds, and sites with higher weighted mean exposure also tend to have lower shear. Now, of course, this is in the absence of the effects of trees. One of the basic concepts with RAMWind is that it is used to define terrain effects on wind speed, not due to trees and so forth. So hopefully the tree effects are all taken out of the data, or hopefully no trees to begin with. And then the mean upwind and downwind exposures are often correlated at MET sites and turbine sites. This is an example of some analysis we have performed at a project site where we have 5 MET towers, and it shows a very close relationship between the downwind exposure and the 60-meter wind speeds, showing positive slope and increasing wind speed with exposure, and then conversely the shear on the right is shown to be negatively related to exposure. In RAMWind version 0.1, this is based on sector-wise analysis, bulk analysis, and we will provide a version in the future that will have sector-wise for doing more refined analysis for wake loss studies and so forth. In RAMWind 1, we can analyze up to 2 wind speeds, shear alpha, and even Weibull K. The per turbine estimates are prepared on for each of these parameters as the user may elect to calculate. And wind mapping is available, and output that is compatible with WASP is also available, so we can take the output from RAMWind and move it into other platforms. These are the references that were mentioned earlier related to 1, the wake loss study where RAMWind was used, and 2, comparisons of modeling software where RAMWind outperformed the other modeling software. And for a free trial version, you can go to our website indicated there, and then download the software and email Liz for a temporary user license. And with that, we will move now to Liz's presentation of the software itself.
All right, hi everyone, this is Liz now. I'm going to be taking you through a quick demo of RAMWind 1.0. Okay, so I'm just going to go ahead and launch the program. And Jack mentioned, this version is available on the website at ramwind.com/downloads. Okay, so when you launch the program, this is the screen that initially shows up, and this is where all of the required inputs are loaded into the program before the calculations can take place. So the first thing that we're going to load in is the topography data. So the topography data is loaded in as UTM, X, UTM-Y, and elevation in just a comma-separated file. And depending on the size of area that you're modeling, it can take a little bit of time for the program to read in all the XYZ data. So it's just loading in this data. Typically, the topography data that we use is 30-meter resolution. We usually download data from the USGS database to do all of our modeling. Okay, so now we're showing the topography data in 3D here, and you'll see this little tooltip that showed up here. It's giving you little tips on how to manipulate the 3D graphics, so you can turn it around, you can change the vertical scaling by clicking these buttons here. Okay, so now we have the topography data, and now we can move on and get the rest of the inputs in. So the next step we're going to do is we're going to import the windrows. So you just click this button here, and we are going to load in the windrows, which is just either a comma-separated or tab-separated file. Load it in, and now we'll see the windrows has been updated. You can always click this button here if you want to actually see the values that you've imported through this text file, and you can change them in this dialog box if you like. And the only requirement is that all of the sectors add up to 1, and then you can go on with your modeling. Okay, so now the next step that we're going to, or the next input we're going to bring in is the Met Tower data. So I found my CSV, which is just comma-separated file. It contains the location of each Met Tower, the wind speeds at 60 meter and 80 meter, as well as the shear coefficient and the Weibull shape factor. So in RAMWind, we can model up to 4 parameters, the 2 wind speeds, alpha, and the shape factor. But you don't necessarily have to model all 3. So if you're only interested in wind speed at one height and say the shear exponent, you can leave the other fields blank, and that will work just fine. And you may have noticed as well that after I imported the Met data, we now have these blue markers showing up on the topography map, and that's showing the locations of the 5 Met towers that we brought in. Okay, next we're going to import the turbine locations that we'd like to model, and this is also just a comma-separated file that has the location and the name of each turbine location. And so after those are loaded up, we now have the list of all of the turbines that we're modeling with their UTM coordinates, and on the map you can see here the turbine locations are showing up in red. Another option here on this tab is you can change the interval, the contour intervals, and the minimum maximum. So for example, say we want a little bit finer resolution, we can change the minimum elevation to say 680, max to 685, and change the interval to 5 meters. Uncheck the auto min max option and click refresh. We'll update the topography map to have the specified minimum and maximum contour level and the interval that you've set. Okay, so this is all of the information that you need to do modeling in RAMWind, and the last table that I'll mention on this tab is the list of radii and exponents shown here. This is the default list of radii and exponents, so the radius varies from 500 up to 5,000 meters in 500 meter increments, and all the exponents are 1.0. And this exponent has to do with weighting between the location of your Met Tower and the surrounding topography, and its weight is the inverse distance to this exponent. So if you like, you can always add or delete radii and exponents from this table just by clicking this button. You can add, say, if you'd like something larger or something in between the default values, you can go ahead and modify this table as you see fit. But for now, we're just going to stick with the default list of radii and exponents. And just so everyone's clear, the reason why we have this range is because we're trying to establish the best empirical relationship between exposure and these wind parameters. And the best empirical relationship will occur at a certain radius. And so we're basically exploring the relationships at many different radii and exponents to see at which radius we get the best empirical relationship. Okay, so I'm going to move on now to the modeling. So the second tab here, right now everything is blank. So what we need to do is we need to calculate the exposures at the Met sites and develop the linear regression relationships. So you just click this button here, and right now it is cranking through all 5 Met sites and performing the exposure calculations. Okay, so now we have some plots and some regression relationships to look at. Okay, so these 3 plots at the top here are showing the relationship between the lower level wind speed and the upwind exposure, the downwind exposure, and the elevation. The second row is showing the relationship between the shear exponent alpha and the upwind and downwind exposure and elevation. The third row is showing the wind speed at the upper level, and then the fourth row is showing the relationship between the Weibull shape factor and upwind and downwind exposure and elevation. This table up here is showing the values that are actually being plotted on the table. So these are the bulk upwind and downwind exposures for the 5 MET sites, along with the elevations at the 5 MET sites. And this table here is showing the linear regression relationships that have been defined at the specified radius and exponent, which is specified in this drop-down table here. So recall in the last tab we had specified a number of radii and exponents to model, and so the plots that are being shown right here are at 5,000 meters. And these are squared and standard error, and the slopes and offsets in this table here correspond to 5,000 meter radius investigation and exponent of 1. Okay, so this is a new feature that was not in the beta version, so for those of you that have used the beta version, this is slightly new. So we modeled the exposure, or we modeled at several different radii, and so if you're curious, at what radii do I get the best empirical fit for a different parameter, you can go to this drop-down menu and select one of the parameters that you've modeled. So say, for example, we're curious about the shear exponent, and we want to see at what radius did we get the best correlation. So you select shear exponent, and then this was automatically updated to a radius of 1,500 meters, at which the correlation was the highest for the shear exponent relationship to exposure. Similarly, if you're curious how at what radius the 80-meter wind speed achieved the best empirical relationship, you just click 80-meter wind speed, and then it updates the plots, goes to 5,000 meters, which is where the correlation was the highest. So you can see in this case we have 5 MET towers, and at 80 meters the relationship between the bulk upwind and bulk downwind versus the 80-meter wind speed is quite high. The R squared is on the order of 0.91. There are situations though where you may not want to include a certain MET tower. It might be an outlier, the data might be suspect, and so instead of just deleting that MET site from the analysis, you can uncheck that MET site from this checkbox here. So say, for example, we don't want to include MET 1. Turn that off, and now you'll notice that this data point has turned gray. It's now not included in the best fit linear regression. And you'll also notice now this table is now blank. And the reason it's blank is because RAMWind is now waiting for the user to really figure out which MET towers to include, and then to recalculate the linear relationships using the specified METs. So say we actually want to keep MET 1, but not include, say, MET 5. So now we've decided, all right, we want to use these 4 MET sites. We're going to calculate linear relationships, and now we have those showing up in the table. Okay, so the plots that we're showing right now are all single parameter models. So for example, this is showing the linear relationship between the 80-meter wind speed and the upwind exposure. But we also create what we call multi-parameter models. So if you were to scroll down in this table here, you can see there are all these single parameter models. So at the top we have, these are all the upwind models for the 4 parameters that we've modeled. And we have the downwind models, again single parameter, and the elevation models. So this is showing the slope and the offset for those single parameter models, as well as the R squared and standard error. But as you scroll further down this table, you'll now see the multi-parameter models. So for example, this one right here is showing a 2-parameter model, so modeling the 80-meter wind speed using both the upwind and downwind exposure. This is showing the R squared of that relationship, and these are the different coefficients and intercept of that empirical relationship. And then we scroll all the way to the bottom, you can see, oh, sorry, we only have 4 MET towers. If you have 5 MET sites, then you can have a 3-parameter model. So down at the bottom here, so here we have the 80-meter wind speed as a function of all 3, being the upwind and downwind exposure as well as the elevation, showing the R squared, the standard error, and then the 3 coefficients as well as the intercept. Okay, so once you've had a chance to look at these plots and the R squared and figure out which model and what radii you want to create models, you can move on to the next step of creating those models. So, actually, we'll start with the 60-meter model. We know that at 5,000 meters, the R squared was high, 0.918 for the upwind and 0.906 for the downwind. So we're going to select the 3 single parameter models, so the wind speed as a function of upwind, wind speed as a function of downwind exposure, and wind speed as a function of elevation. And then we're also going to select the 3 parameter model. So just by holding the control key, you can go through the table and select the models that you'd like to use, and then click Add Model. And then this little dialog box will pop up with a suggested name for the model, and I'm just going to accept the automatically generated name. And we have those models specified in this table down here. I'm going to do the same sort of thing for shear exponent. At 1,500 meters, that's where the best correlation was found for alpha. And going to do the same sort of models. We're going to select the 3 single parameter models for the shear exponent as well as the 3 parameter model. We're going to accept all of the automatically generated names, and now we have those models in our table. And finally, we're going to create models for the 80-meter wind speed using the same sort of approach, the 3 single parameter models and 1 3-parameter model. And for this demo, we're not going to do the Weibull shape. We'll just stick with the 2 wind speed and shear exponent models. So once you have those defined, the next step is to generate estimates at the turbine locations using these models. So all you do is just click this button here, and what the program is doing is calculating exposures at all of the turbine locations you've loaded in and generating 60-meter estimates, alpha estimates, and estimates of the 80-meter wind speed based on all the models that specified. Once the calculation is finished, will redirect us to the turbine estimates tab. Okay, so now on this tab you can look at all the results of the models that you created. So this drop-down box here is showing all the models that we specified in the previous tab, and so you can select any one of them and take a look at what the estimates of the turbine locations turned out to be. So for example, if we look at the 80-meter 3-parameter model, you can see the 80-meter wind speed modeled at the turbine locations, which are shown in red, and the 80-meter wind speed at the Met locations are shown in purple. This plot here is showing the upwind exposure as a function, or the 80-meter wind speed as a function of upwind exposure, and then the 80-meter wind speed versus downwind exposure, and then versus elevation. In this table here, we have the individual turbine locations and their modeled parameters, so you can scroll through and see how the different models, the different estimates that they generated. And then the statistics of the turbine locations are all shown on here. So the average, the standard deviation, min-max, and the count. And then there's also exceedance count, which I will now discuss what we mean by exceedance and what this exceedance algorithm drop-down box refers to. So to best demonstrate that, we're going to look at shear exponent model. And so this is showing the shear exponent as a function of upwind exposure. And again, the red dots are all of the turbine locations, and the purple dots are the Met locations. And the exceedance algorithm that we've selected right now is called ignored. So basically what that means is that if the exposure of the turbine location is outside the bounds of the exposures of the Met locations, the same linear regression relationship is used, and the fact that the turbine location has an exposure that exceeds the Met tower, that's ignored. Another way of dealing with the exceedance is to cap it. So you can go to this drop-down box and click cap, and what happens is if the turbine location's exposure exceeds the limits of the Met sites, then either the minimum or the maximum exposure of the Met site is used. So the turbine location alpha cannot exceed the limits of the Met location. And then the third option for exceedance is called combined. And this is just simply an average of the ignored algorithm and the capped algorithm. And so it gives a slightly more conservative estimate than the ignored algorithm, but not quite as harsh as the capped algorithm. So this is actually what we typically will use in cases of exceedance. The last thing to talk about with exceedance is when there's a multi-parameter model. So this is now showing the modeled shear exponent based on the 3-parameter model, so based on upwind, downwind, and elevation. And so now in this exceedance drop-down menu, there's a 4th option, which is called linear. And so if the linear exceedance algorithm is used, then if the exposure is outside the bounds of the met site's exposures, then the linear or the single parameter models are used in cases of exceedance. Okay, so that might have been a lot to take in. Again, this is all going to be available on the website later, so if you'd like to review it, feel free. And also in our user's manual, the concept of exceedance and the different algorithms are also covered. Okay, the last feature on this tab that I'd like to point out is the export button. So often after the exposures have been calculated at the turbine sites and the met locations, often we'd like to bring them into Excel or other programs to do further analysis. So by clicking that button, it opens up this dialog box, and then you can select which radius or radii to export, which turbine locations you'd like to export, and the met sites. And so when you click export, it generates a CSV file that you can then bring in quite easily into Excel to do further analysis. Okay, so this tab here shows the results of all the models that you've created. And then the next 4 tabs are all quite similar to one another, and they separate out the wind speed or the estimates based on the parameter type. The first tab here is showing the results of all of the 60-meter wind speed estimates. The tab is showing the results of all the shear exponent estimates and 80-meter estimates. And then the last tab, or the second to last tab, is the Y-bowl estimates, which we have not done in this case. So as I said, all 4 of those look quite similar. And so what you see on each tab, first of all, is a summary of all of the models that you created for the 60-meter wind speed in this case, along with the exceedance algorithm that was specified, and then some statistics of the turbine, or the estimates of the turbine location. So the average 60-meter wind speed, min-max, and standard deviation. The table over here shows the individual turbine estimates generated from each of the models specified in this table. So for example, model number 1 is the 60-meter wind speed as a function of upwind exposure with an ignored exceedance algorithm. And so the turbine estimates that correspond to that model are shown in the second column here. Another feature that we find quite useful, because often this table can get quite crowded with all the different exceedance algorithms that are generated. So if we are only curious in, say, the combined exceedance algorithm, then you can select all of the other models that you might not be interested in at this time, select them all, and then click Hide. And so now we are only displaying the models with the combined exceedance algorithm. So it just cleans it up a little bit and helps to, it's easier to look at that way. Okay, another feature that we use quite often is combining models by the R² of the linear regression. So I've selected all 4 of these models, and then I'm going to click this button here that is going to take those 4 models and combine them into one average model. So here is an automatically generated name that has appeared, and it can get pretty lengthy. So instead of using that name, we're going to say no, and we're going to create our own, and I'm going to call it combo meter wind speed, and then I'm going to say okay. And so now we have this 5th model, that again is a combination of the first 4 by each model's R². Now, since this model name is not very descriptive, we have a little box down here where you can keep notes, which is useful for trading files with colleagues, or when just going back and trying to remember what it was that you did. So I'm going to write combo 60-meter wind speed as an average of the upwind, downwind elevation model and the 3-parameter model. And these notes are saved in the file. So speaking of which, it's always a good idea to save your work. So I'm just going to go ahead and save this model. We'll call it something else. We'll call it example model 2. Saves it as a .bl, we call it the file. So once saved, you can share the file with other people, and they can load it into RAMWind and have a look at the modeling that you did. Okay, so the last thing to mention on this tab are the 2 different export functions. So you can either export the turbine estimates as a CSV, so you have to select one to export. So say we'd like to export the combined, the averaged model. So you check off that model, export, and then it takes you to, and you just save it as a CSV. And then you can bring it into Excel or whatever other program you'd like to use for further analysis. And then the other export option is to export as a .rsf, which is compatible with WindFarmer, WindPro, and other sorts of wind analysis programs. Alrighty, so the Alpha Estimates tab is very similar to what we were just looking at. You can do the same sort of averaging of models by selecting the ones that you'd like to use and combining them, weighting them by each model's R-squared. And you can also export the selected model as a CSV. Next tab here is showing the 80-meter wind speed estimates, and it's, again, very similar to the previous 2, but there is one additional feature that we should go over, and that is this button right here, where you can extrapolate wind speeds from the lower level using an alpha model to generate wind speeds at your second level. So when you click that button, it opens up this dialog box, and it shows a list of all the 60-meter wind speed models that you've created, as well as all of the shear exponent models that you've created. So let's say we want to use the combination 60-meter wind speed model and the 3-parameter shear exponent model with the combined exceedance. And we'll give it a name. We'll call it extrap 80-meter wind speed. And using a 60-meter wind speed model and the specified alpha model, we've now generated a new 80-meter wind speed estimate based on those 2 other models. And so here we have the statistics of that extrapolated model. And if you scroll over to the right here, you can see the list of all the different turbine estimates based on that model. And again, always a good idea to make notes for yourself or others about what it was or what models were included in the extrapolation. Okay, and so in that you can export as CSV, or you can export as a .rsf. Okay, now the last feature that we're going to talk about is the mapping capability of RAMWind. So on this tab, you can generate 2 different types of maps. You can generate a map of exposure, or you can generate maps of the wind parameters that you've modeled. It can take a little bit of time to generate these maps, and so instead of doing that here, I'm going to go ahead and open the file that I created earlier that has some of the maps already created. So one thing that we're finding really quite handy is to generate maps of exposure, and that is really useful at the beginning stages of looking at a site and trying to figure out the best location for MET sites. Typically what you want to see is you want the MET sites to have a good range of exposures that would represent all of the turbine locations that you're planning on siting. So for example, this model here is showing the downwind exposure at a 200-meter resolution. And on the plot here, we're showing all of the MET sites in blue, the turbine locations in red, and the different exposure levels are shown as different colors. So if we want to maybe look at it in just 2D, it might be a little bit easier to see. And we can also change how the contours are being plotted. So if we go from minus 20 meters of exposure up to 30 meters of exposure at an interval of 2 meters. Again, there we go. So now you can see how exposure varies across your site. And then you can also export the map as a CSV. So again, you can load that information into Excel if you're trying to microsite and pick out the best location for your MET sites to have, a certain range of exposure. Then the other type of map that you can create is based on wind speed. And so you would click this button here to generate that sort of map. And on this tab, you specify the type of model that you want to create. So say, for example, if we were to create an 80-meter wind speed map, select that model type, and then select the model that you'd like to use. And then here you can specify the UTM min-max, so the area that you'd like to model. You can also specify the grid resolution. So, typically we would start with a fairly coarse resolution, and then as we're doing more and more detailed micrositing, we would reduce that grid resolution to something smaller, to maybe 20 or 30 meters. But again, this can take a little bit of time to chug through all the calculations. So I've already created some maps, and so this is showing, let me turn on the auto contouring, there we go. So this is displaying the 60-meter wind speeds as a function of the downwind exposure, calculated at a radius of 5,000 meters. All the red dots here are showing the turbine locations, and the blue are showing the MET sites. If you're not interested in looking at those, you can always come off like so. And then you can also look at it in 3D, which it can be quite useful. So you can turn it around. If you like, you can zoom in, different locations, and that sort of thing. And finally, you can export these maps as a WRG file by clicking this button, which generates files that you can then bring into other softwares like WindPro, WindFarmer, and that sort of thing. And also down here we have statistics of the maps that were generated, including the average, standard deviation, min-max, number of data points, and how many of those data points exceeded the exposures of the MET locations. Okay, so I think that about sums it up. Again, if there are further questions, please feel free to email me at liz@ramwind.com. And the download for this software can be found at ramwind.com/downloads. And once you get the setup file, just send me a quick email and I'll get you a temporary user license, which is good for 30 days. And that's 30 days of use. That's not in calendar days. So if you download it but don't actually have to use it for a little while, that it won't expire in a month. It's 30 days of actual usage. So I think that about concludes the webinar. If there are more questions, again, feel free to email, and maybe I'll just turn it back over to Jack in case he has anything additional to say.
Not a whole lot. Thank you, Liz. Very good job. And I'd like to thank Liz very much for her excellent job coding up RAMWind. We are in constant process of adding more features. So this is just version 1.0. We already have some ideas on version 1.1. And in version 2, we'll likely be adding wake loss calculations, and we will be adding sector-wise analysis, which, as I mentioned before, is very useful for doing very refined analysis of wind speed variation by in specific wind direction sectors. So it's a constantly developing, evolving product, and we also invite you all to please give us feedback on features that you like, or any suggestions you might have to make RAMWind more useful to you. We're very interested in hearing from you about that. So thank you very much for your time and attention. We appreciate the fact you've taken time from your day to hear this presentation and see it, and we hope you will try RAMWind because we have been very, we're very pleased with what it can do. There's so many very many sites. We get really good fits, and it can help reduce uncertainty in wind speed estimates for the project sites. We're firmly convinced of that. So thank you again, and hope to hear from you. Take care. Bye-bye.